Nobel Prize-winning physicist Adam Riess recently acknowledged that our current understanding of the universe remains incomplete. He pointed to a puzzling discovery made by the James Webb Space Telescope, one that highlights, yet again, how the cosmos doesn't behave according to our established models. So why is the universe expanding significantly faster than our standard theories predict? This long-standing issue, known as the Hubble Tension, has baffled scientists for years. Now, researchers from the universities of Bonn and St. Andrews believe they've uncovered a solution to this cosmic conundrum. But there's a catch. Their groundbreaking explanation only holds up if we're willing to let go of Albert Einstein's foundational ideas about gravity. Today, we're diving into what the James Webb Space Telescope has uncovered from the farthest reaches of the cosmos, and how one intriguing alternative theory might offer a solution to one of science's biggest mysteries. In less than 3 years since its mission began, the most powerful space telescope ever launched has already challenged much of what we thought we knew about the universe's evolution. If you've been following the news, you've probably seen that Webb has revealed a number of mysterious galaxies, immense and massive, appearing just a few 100 million years after the Big Bang. These early cosmic giants defy our current models, earning them the dramatic nickname, universe breakers. But is that nickname truly fitting? Maybe not, because the situation might not be as impossible as it first appeared. A new research study suggests that these mysterious red objects aren't monstrously massive galaxies after all. Instead, they seem to be growing black holes. If most of the observed light is actually coming from these strange, dense objects, then we're not dealing with premature galaxies that threaten to unravel our entire cosmological model. While further observations are needed to confirm this explanation, it appears we're heading in the right direction. Unfortunately, the same can't be said for another major issue in cosmology. As mentioned earlier, the universe is expanding significantly faster than our current theories can account for. We have Edwin Hubble to thank for the groundbreaking discovery that the universe is expanding. About a century ago, he realized that the Milky Way isn't alone. Countless other galaxies exist, and they're all moving away from us. This revelation led to an even more profound insight. If we rewind time, the expanding universe must have originated from a single, incredibly dense point. This point, now known as the original singularity, became the foundation of the Big Bang theory. But the surprises didn't end there. In the 1990s, scientists found that the expansion of the universe isn't just continuing, it's speeding up. This unexpected acceleration led to the theory of dark energy, a mysterious force believed to oppose gravity and drive the universe's rapid growth. How fast is the universe actually expanding? At first glance, this might seem like a straightforward question, but in reality, it's central to a long-standing puzzle that astronomers have been working to solve for years. The issue, known as the Hubble Tension, presents a challenge from a theoretical perspective. Theoretically, the situation appears clear. When we use the Standard Model to calculate the Hubble constant, which measures the current rate of expansion of the universe, we arrive at a value of approximately 67 kilometers per second per megaparsec. The unit might sound unusual, but keep in mind that a megaparsec is about 3.26 million light-years. This means that galaxies are moving away from each other at an increasing speed of 67 kilometers per second for every 3.26 million light-years. In simpler terms, that's roughly 244,000 kilometers per hour per megaparsec. Unfortunately, this holds true only in theory. In practice, our direct measurements in space have revealed that the Hubble constant is much higher. Specifically, studies involving supernovae, gravitational lenses, variable stars, and red giants have determined that the value is actually 73 kilometers per second per megaparsec, equivalent to about 264,000 kilometers per hour per megaparsec. This represents a deviation of at least 20,000 kilometers per hour per megaparsec from the theoretical prediction. This significant discrepancy is referred to as the Hubble tension. But what could explain this? Could it be that past measurement errors have skewed the true value of the Hubble constant? That's precisely what experts aim to investigate when they used the Webb Telescope to reassess the data gathered by the Hubble Telescope. To investigate this, a team led by Nobel Prize laureate Adam Riess from Johns Hopkins University in Baltimore examined variable stars, red giants, and a group of carbon-rich giant stars. In doing so, they discovered that the significant gap between theory and observation persists. The analysis of the most comprehensive dataset from the Webb telescope to date also resulted in an overall measurement of 72.6 kilometers per second per megaparsec. This means the deviations from the standard model cannot be explained by measurement errors or inaccuracies from the Hubble Space Telescope. Adam Riess summarized the findings, stating, "The discrepancy between the observed expansion rate of the universe and the predictions of the standard model suggests that our understanding of the universe may be incomplete." With two NASA flagship telescopes corroborating each other's findings, the discrepancies in the Hubble constant must be taken seriously. But what might be causing this issue? In other words, if our current understanding of the universe is incomplete, what have we missed? According to Riess, the answer could lie in an exotic form of dark energy or dark matter, the discovery of a new particle or field, or even a flaw in our understanding of gravity. Could Einstein have been wrong? The research team from the universities of Bonn and St. Andrews suggests that gravity might behave in ways we haven't yet considered, offering a potential solution to the Hubble tension and a simpler explanation for this cosmic puzzle. The proposed solution hinges on the assumption that the Milky Way is situated within a supervoid, an enormous, nearly empty region of space. Large-scale astronomical surveys have revealed that the largest structures in the universe are not chaotic or randomly distributed, rather, they are intricately arranged in a network-like pattern. This network forms what are known as filaments, which, along with the vast voids, create colossal, almost matter-free bubbles across the cosmos. According to a study spearheaded by Sergei Mazarino, the Milky Way is positioned within one of these massive voids. This framework provides a compelling context for understanding the so-called Hubble tension, offering an explanation for this cosmic conundrum in a remarkably short time. To explain this concept, the researchers liken the constellation to an air bubble embedded in a cake. Because the matter density surrounding the bubble is significantly higher, it creates gravitational forces that pull galaxies inward, toward the bubble's edge. When applied to the mystery of cosmic expansion, this suggests that galaxies are receding from us much faster than anticipated due to the influence of a local underdensity. However, this seemingly reasonable explanation comes with a major drawback. According to the standard model, such underdensities or supervoids shouldn't exist, as the model predicts matter in space should be uniformly distributed. Nevertheless, the study's authors point to a group of galaxies 600 million light-years away, which are moving away from us at a rate 4 times greater than what the standard model predicts. But that's not the full story. In the same breath, the scientists highlight that the standard model of physics, which we rely on to explain many fundamental forces in the universe, is built on a framework of gravity originally proposed by Albert Einstein. However, they point out that it's entirely possible that Einstein's theory of relativity, despite its monumental success, might be incomplete or even incorrect in certain key areas. More specifically, the assumption that gravitational forces behave exactly as Einstein predicted might not be entirely accurate. This brings us to the modified approach that these researchers have incorporated into their computer simulations. The theory in question is called modified Newtonian dynamics, or MOND for short. Proposed in the 1980s by Israeli physicist Mordechai Milgram, MOND challenges some of the core principles of classical gravity and is considered an outsider theory in the scientific community. Yet, it has gained traction for offering potential explanations for phenomena that remain puzzling under Einstein's original framework. MOND, modified Newtonian dynamics, provides an alternative explanation for the rotational behavior of galaxies by altering the equations governing the motion of matter within a gravitational field. This theory suggests that dark energy, often proposed to explain certain cosmic phenomena, may not be necessary. Instead, MOND proposes that the inconsistencies we observe in galactic rotations can be explained by modifying how gravity works at large scales. One of the intriguing predictions of this theory is the existence of vast, empty bubbles in space. This idea is at the heart of the theory's challenge. If gravity behaves in the way MOND suggests, there could be a single constant that governs the rate of cosmic expansion, with the apparent discrepancies in motion being attributed to the uneven distribution of matter across the universe. The question remains, however, whether MOND can break free from its current status as a fringe theory and gain wider acceptance in the scientific community as a viable alternative to our current understanding of cosmic dynamics. The future will reveal whether MOND can overcome these challenges and reshape our view of the cosmos.